Hello everyone, welcome back to Solid State series. This is video number 14, and in this video I'm going to talk about voids in a BCC unit cell, voids in body-centered cubic unit cell. Actually, there are two types of voids in a BCC unit cell. One is distorted tetrahedral voids, another one is distorted octahedral voids. So in this video, we are going to answer some questions like where the voids are present, why they are distorted, how many voids are present in each unit cell, what is the radius of that void. These are the things we are going to answer in this video. So first, let us discuss distorted tetrahedral voids in a BCC unit cell. So firstly, BCC unit cell, the unit cell has particles at the body centers and corners. And here, in order to understand the voids in BCC unit cell, it is necessary to take two adjacent unit cells. This is one BCC unit cell. This is another BCC unit cell. But we know that in BCC unit cell, particles are present at body center and corners, all corners. But here, all corners are definitely occupied by the particles. But to understand only any two corner particles of an edge are sufficient. So here, this is the first unit cell and this is the second unit cell. And this is body centered particle. This is body centered particle. And this is corner particle. And this is also corner particle. To identify tetrahedral void, I have taken these two corner particles which are separated by a distance a, and these two body center particles, these are two are also separated by the distance a. So the distance between these two body centers also, that is a. And here these four particles of adjacent unit cells, like two corner particles and two body center particles, these four particles are forming a tetrahedron. These four particles are forming a tetrahedron. But that tetrahedron is not a normal tetrahedron, that is irregular or distorted. That is irregular. Why it is irregular? Why it is irregular? Because here, if you take this length, this edge length, if you take, that is A. This edge length, if you take, that is A. But here, this is corner particle, this is body center particle. The distance between the corner particle and body center particle is half the value of a body diagonal. Body diagonal is root 3a, and the distance between these two particles will be root 3a by 2. So you know tetrahedron has 6 edges, but in this tetrahedron, all edges are not have the same length. See, this edge is having the length a, this edge is having the length a, but this edge is having the length root 3a by 2. This is another edge actually. This edge is also having the same length, that is root 3a by 2. This is fifth edge, root 3a by 2. This is another edge, that is also root 3a by 2. Out of 6 edges, 2 edges are having the length a, remaining 4 edges are having the length root 3a by 2. Hence, the tetrahedron formed by these 4 particles is not normal, that is irregular, that is distorted, irregular tetrahedron. Now, what is the exact position of tetrahedral void if you observe? So whatever the irregular tetrahedron formed by these two corner particles and two body center particles, at the center, the point T, you can see here the point T, this point is tetrahedral void in BCC unit cell. But this tetrahedral void is not a normal tetrahedral void. This is a distorted tetrahedral void. Distorted tetrahedral void. So here, at what position it is placed, it is present if you observe carefully. So here, let me take the center of point between these two body centers. This is the point P. In fact, this is the common face, and this point P is the face center of this common face. And the center of these 2 points, if you take the center of these 2 points, if you take, that is the point, this is the point, and this point is actually edge center. That point is edge center. So what I have taken here, one is center of the point between these two body centers I have taken, which is face center, and the center of these 2 points I have taken, which is edge center. And now I have to take the midpoint of this edge center and face center. That midpoint of that face center and edge center is a tetrahedral void, but it is not a normal tetrahedral void. It is a distorted tetrahedral void. Why it is distorted tetrahedral void? Because the tetrahedron formed by these 4 particles is not having the same edge lengths. It is having 2 different types of edge lengths. Now we have to find the radius of this tetrahedral void. If any atom occupies this tetrahedral void without any distortion, which atom with maximum radius, which is going to sit in the tetrahedral void, we are going to find. Simply, we are going to find the radius of the tetrahedral void. In order to find the radius of the tetrahedral void, of course, we have to take this triangle. The triangle is BTP. So that is body center particle, and P is a point which is actually a face center. That is not a particle, that is a point. And T is a tetrahedral void. T is a tetrahedral void, and we need to find the radius of that particular tetrahedral void. And first, before going to the radius of the tetrahedral void, how many such tetrahedral voids are present? Let us take this kind of tetrahedral void. So very clear, from this edge center to this point, that is a by 2. From this edge center, this value, this point to this point, the distance is a by 2. And from this point to edge center to tetrahedral void, that will be obviously a by 4. A by 4. Tetrahedral void is located between edge center and face center, exactly at the midpoint. And from edge center to tetrahedral void, what is the distance? That is a by 4. The most important thing you have to notice, such kind of tetrahedral voids are formed at 4 places of the face. Not only at this position. There is a tetrahedral void here. There is a tetrahedral void here from this edge center to a by 4 distance, from this edge center to a by 4 distance, from this edge center to a by 4 distance, because here this is also a tetrahedral void because surrounded by 2 corners of this and 2 body centers. So what I'm trying to convey is this kind of tetrahedral voids, if you observe, every face of BCC unit cell has 4 such tetrahedral voids. Where exactly they are located means they are at the midpoint of edge center and face center. Edge center is not a particle, that is only a point. Face center is not a particle, that is only a point. And like this, there will be 4 tetrahedral voids on each face. Each face. But BCC, it is basically a cubic unit cell. How many faces are present? 6 faces. Each face has 4 tetrahedral voids. That means 6 into 4, that is equal to totally in one unit cell of BCC, there are 24 tetrahedral voids, but effective number we need, because they are present on faces. When the void or particle is present at face, that is equally shared by 2 unit cells. For example, you see this tetrahedral void. This tetrahedral void is shared by left side unit cell and also right side unit cell. As a result, the contribution of this tetrahedral void will be 1 by 2. A total number of 24 tetrahedral voids, but the contribution of each tetrahedral void is 1 by 2. Hence, we can say 24 into 1 by 2, that is equal to, effectively, each BCC unit cell has 12 tetrahedral voids. Each BCC unit cell has 2 tetrahedral voids. Actually, how many atoms are present effectively in BCC unit cell? 2 atoms. How 2 atoms? Body center atom is 1. 8 corner atoms, 8 into 1 by 8, that is 1. So 1 body center, effectively 1 corner. So BCC unit cell, rank of BCC unit cell is 2. That means effectively there are 2 atoms. For 2 atoms, there are 12 tetrahedral voids. For 2 atoms, there are 12 tetrahedral voids. And for 1 atom, obviously, there will be 6 tetrahedral voids. So the number of tetrahedral voids per atom in BCC unit cell, but most importantly, I'm using the term tetrahedral, but initially I clearly clarified that it is not a tetrahedral void, it is a distorted tetrahedral void. Of course, I may be using tetrahedral void, but by default it is a distorted tetrahedral void. How many distorted tetrahedral voids are present? 12 distorted tetrahedral voids in 1 unit cell of BCC. In 1 unit cell of BCC, there are 2 atoms effectively. So each atom is going to produce 6 tetrahedral voids. That means 6 tetrahedral voids per atom. That is the calculation. Why? Where is the tetrahedral void? What is the position of tetrahedral void? How many such tetrahedral voids are present? Why it is a distorted tetrahedral void? And the last point or the last question we have to answer in tetrahedral voids, that is, what is the radius? What is the radius? And here you can see the edges, one is a, another one is root 3a by 2, and totally there are 24, but effectively there are only 12, and here 6 tetrahedral voids per atom in BCC unit cell, but it is already told you it is a distorted tetrahedral void. Now we have to find the radius ratio. We need to find the radius ratio. In order to find the radius ratio, I'm going to take this triangle out. What is this triangle? Body center, face center, it is a point, tetrahedral void. Now it becomes a triangle BPT. Body center to face center, what is the distance? A by 2. Tetrahedral void to this face center, the distance is a by 4 according to the diagram. That is a by 4, and now very easily we can calculate this radius ratio. So this is body center, this is a point face center, this is tetrahedral void, and this is called distance between body centered atom and tetrahedral void, and that point, that value I'm taking as d, and body center to face center it is a by 2. From face center to tetrahedral void it is a by 4. Again, from that Pythagoras theorem, d square is equal to a by 2 whole square plus a by 4 whole square, and this d square is equal to a square by 4 plus a square by 16, which is equal to 5a square by 16, and d is equal to root 5 by 4 times of a. But do you remember the relation between edge length and radius of atom which is forming the unit cell? BCC, do you remember? Root 3a is equal to 4r. Root 3a is equal to 4r. In case of a BCC unit cell, if you take a body diagonal, the particles along the body diagonal are present like this, and this is the particle which is forming BCC unit cell. This is body diagonal. Body diagonal is root 3a. Root 3a is equal to 4r. And here, this distance, here body center and the tetrahedral void are obviously in contact. I told you, the atom which is going to sit in the tetrahedral void will be in contact with this body center atom. So that d is equal to radius of atom which is forming BCC unit cell and radius of tetrahedral void. Radius of tetrahedral void. And in place of d, let me take this r, capital R, radius of the atom, and small r, that is radius of tetrahedral void, which is equal to root 5 by 4 times a. But in place of a, I'm going to substitute 4r by root 3, and here this 4 is getting cancelled. Our intention is finding radius ratio. So send this radius term, capital R, opposite side, and it becomes So here this is root 5 by root 3 minus 1. It will be like radius of tetrahedral void is 0.29 times of radius of sphere. The very interesting point here you are going to know, that is, in case of CCP, or HCP, radius of tetrahedral void, if you can recollect, that is equal to 0.225, nearly that is 22.5 percentage. Radius of tetrahedral void is nearly 22.5 percentage of radius of atom which is forming that particular lattice. But in case of radius of distorted tetrahedral void, is nearly 29 percentage, 0.29 into radius of atom which is forming BCC unit cell. So finally, the points: where is tetrahedral void? How many tetrahedral voids are present per unit cell of BCC? What is the radius ratio? Okay, you can bring this capital R this side, that becomes radius ratio. So this is about a tetrahedral void, and this is not a tetrahedral. Basically, it is distorted tetrahedral void. And now let us complete this discussion with octahedral void. There are also some other voids called octahedral void. Do you remember octahedral void is surrounded by how many particles? 6 particles, 6 corners, because octahedron has 6 corners. Octahedron has 6 corners. But why these are distorted again? What is the reason for that? Let us discuss. And most importantly, distorted octahedral voids are located at 2 places. One is face center, another one is edge center. But we have to understand how face center of BCC unit cell is a distorted octahedral void, and why it is distorted octahedral void. Not only face center, even edge center is also, what do we call, distorted octahedral void. First, let us understand that. So for example, again, no doubt, if you want to locate octahedral voids, again you need to take what do we call minimum 2 unit cells. Then only you can understand, then only you can see, then only you can locate. So face center is an octahedral void. In order to prove that, I am taking 2 adjacent unit cells, and you know BCC unit cells, the particles are present at body center and corner, and this is the common face. You can see this is the common face, and if you carefully observe, this common face has 4 corners. I'm taking the 4 particles like this, and this body center and this body center, this body center and this body center. And here, if you take, this is a distance between corners, that is A. This is distance between corner, that is A. And of course, this is also distance between corner, that is A. And here, body center and the body center, the distance between these 2 body centers also, what do we call a A. Now, these 4 corners which are present on the common face and 2 body center atoms are forming octahedron. You have to imagine octahedron in these 2 adjacent unit cells. Now you have to see only this diagram, then you will be comfortable and you can understand how it is octahedron. Octahedron is also square bipyramidal. This is a square, for example, and here this is one pyramid, and here this is one pyramid, and here this is another pyramid. This is another pyramid. Now this face center you can see. This face center is surrounded by 2 body centered atoms, 4 corner atoms. Altogether this is surrounded by 6 spheres, 6 atoms. Hence this is what do we call octahedral void. Octahedral void is formed by 6 spheres. But the point is, why it is distorted? Why it is distorted? If you take from this face center to body center, if you take, From this face center to body center, what is that distance? That is a by 2. A by 2. Of course, this is also a by 2, no problem. But if you take the distance between this octahedral void and corner atom, what is this distance? This distance is half the value of phase diagonal. Half the value of phase diagonal. Do you remember, from this corner to this corner is phase diagonal? Phase diagonal is root 2a, and half the value, that is root 2a by 2. Root 2a by 2, that is a by root 2. Again, you can see they are not having the equivalence. They are not having the equivalence. We can say this is what do we call distorted octahedral void. Distorted octahedral void. And not only in that way, the distance between this octahedral void, body centered atom, is a by 2. Octahedral void and another particle, that is corner of the cube, and here that is, what is the distance? A by root 2. A by root 2. Not only in that way, there is one more point. If you take this edge A, this edge A, this edge A, this edge A, but this is one edge of octahedron. This is one edge of octahedron, and this corner to body center, what is the distance? That is half the value of body diagonal, that is root 3a by 2. So because of these two reasons, we can say that this face center is octahedral void, but it is not a normal, that is distorted octahedral void. This is one position. And another position is not only face center, even edge center is also an octahedral void. But in order to feel this, you need to take 4 unit cells. 2 unit cells are not sufficient. You need to take 4 unit cells. Now this is 1, 2, 3, 4 unit cells, and these are the, what do we call, body centered atoms of 4 unit cells. Body centered atoms of 4 unit cells. And here now you can see this is the square. This is the square with the 4 body centers. This is the center of the square. This is one pyramid. This is another pyramid. What happened? Square bipyramidal. Square bipyramidal. The 4 body centers of these 4 unit cells are occupying the 4 corners, and this corner and this corner are occupying the remaining 2 corners of octahedron. I'm talking about octahedron. The octahedron you have to visualize in these 4 BCC unit cells. These 4 body centered atoms, and this is edge center we are talking about, and the 2 corners of this particular edge, if you want, you can see here, this is what we call a square. So that is 4 corners of 4 unit cells, and this is edge center point. And here we have one corner, here we have one corner, this corner, and now you can see this particular thing is again said to be, what do we call, octahedral void. So edge center is an octahedral void, face center is also an octahedral void, but this is also distorted. Why this is also distorted? You can see from this edge center to this, the distance is a by 2. From this edge center to, what do we call, body center. From this edge center to body center, definitely the distance is not a by 2. That will be, what do we call, a by root 2. Hence, this is also what we call distorted octahedral void. So we have taken the proof. Now we need to count the number of such octahedral voids, okay, distorted octahedral voids. Finally, the radius ratio. So what is the conclusion? Face center and edge centers are distorted octahedral voids. And how many such octahedral voids are present? How many such octahedral voids are present? See, face centers are how many? 6. But what is the contribution of a face center? 1 by 2. So that is 6 into 1 by 2. 6 into 1 by 2. And edge centers are how many? 12. Edge centers are 12. What is the contribution of edge center? 1 by 4. So 12 into 1 by 4. So here this is 3, this is 3. So totally we can say there are 6 distorted octahedral voids in one unit cell effectively. Effectively, there are 6 octahedral voids. Effectively, there are 12 tetrahedral voids. Number of octahedral voids effectively in one BCC unit cell, that is distorted only 6, and this is 12. So here this is about the number. Now finally we need to find the radius ratio, but it is somewhat easy to find the radius ratio. I'm going to take so here body center, and this is what we call a distorted octahedral void. This is body center, and I'm going to this body center and this octahedral void are definitely in contact, and with the help of that I'm going to find the radius ratio, and here is the radius ratio. So here radius ratio, this edge length is equal to, so this is body center, this is body center, this is face center. Face center is a void. Which void? Distorted octahedral void. Now from this picture you can see this is edge length. Which edge length is equal to 2 times of radius of particle and 2 times of radius of octahedral void. You can see the diagram. So this is radius of atom, this is diameter of octahedral void. And you already know in BCC unit cell, root 3a is equal to 4 times of radius of particle. And from this a is equal to 4r by root 3. And our intention is very clear, finding the radius ratio. Remaining things, mathematical rearrangements. This is cancelled by 2 times. So that is 2r by root 3 is equal to r plus r naught. And here send this r opposite side. You'll be getting r naught. So this is r naught is radius of octahedral void, ro, r naught, whatever. And this r naught is equal to r is common. 2 by root 3 minus 1 times of that is times of r, and this is this value is 2 by root 3 is 1.154 minus 1, that will be 0.154. Surprisingly, in case of BCC unit cell, radius of octahedral void is 0.154, whereas in a cubic close packing structure or HCP structures, radius of octahedral void is 0.414 times of radius of a sphere, whereas in BCC this value is 0.154 times of radius of sphere. That means, conclusion, if you see, according to the data, tetrahedral void is bigger in size when compared to octahedral void. And this is about types of voids in octahedral, types of voids in BCC structure, tetrahedral and octahedral voids. And this is the end of this video. And we'll be meeting in the next video. Thank you. Thank you very much.